In the last video, we talked about energy and how the energy in a system can be changed by the addition or removal of heat, or when work is done on the system, or when the system does work on the surroundings. When we talk about these energy changes, we always talk about them from the perspective of the system, where the system is defined as the thing that's changing. And this could be a chemical reaction or a phase change or another change where bonds are being formed and broken, or where intermolecular forces are forming or overcome. But one of the things that can be a little confusing is that when we are measuring energy changes, we're typically measuring the surroundings and not the system. Think about it. You can't stick a thermometer or your hand into a chemical reaction or into a phase change. We can't stick a temperature probe into the bonds that are breaking or into the intermolecular forces that are forming. This is just not possible. But what we can directly measure are the changes that are happening in the surroundings. Remember, we are part of the surroundings. Our thermometer is part of the surroundings. The solution that things are dissolving into is also part of the surroundings. In short, although we can't actually be inside the system, we can infer what is happening inside the system by measuring what is happening in the surroundings. Now let's talk a moment about the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed, but it can be moved from one place to another or transformed from one type of energy to another type. When energy moves from the system to the surroundings or from the surroundings to the system, the amount of energy gained or lost by the system must be equal to the amount of energy gained or lost by the surroundings. And this is why we can determine what's happening inside the system by knowing what's going on in the surroundings. However, when we're talking about energy flow, what's going on in the surroundings is the opposite of what's going on in the system, and this is what makes things confusing. As we said in a previous video, chemical and physical processes that result in energy changes are defined as either endothermic or exothermic, depending on whether energy is gained or lost by the system. In endothermic processes, energy is gained by the system. Heat enters. Energy comes into the system from the surroundings by heat transfer, or energy comes into the system by work done on the system. Common examples are adding heat to something or warming something up, chemical reactions that absorb heat from the surroundings, vaporization, because remember, energy must be absorbed for a liquid to change into a gas. Even though the system is gaining energy, the temperature we measure in our surroundings will be colder than it was before the reaction took place. The heat that the system is absorbing is coming from the surroundings. In other words, the surroundings are giving up heat to the system. When you hold a cold beverage in your hand gets cold because the system, the cold beverage, is absorbing heat from you. In endothermic processes, the surroundings get colder. In exothermic processes, energy is lost by the system. It goes out of the system. Energy exits. Energy is transferred from the system to the surroundings through heat transfer or through work done by the system on the surroundings. Some examples include the release of energy when bonds are formed, the release of energy when intermolecular attractions form. Energy is released in freezing and in condensation. Energy is lost in the form of work when gases expand, and this is because the system's doing work on the surroundings. During an exothermic reaction, the temperature we measure in the surroundings is warmer than before the reaction took place. The energy lost from the system during the chemical reaction has heated up the surroundings. Your hand on the beaker gets hot because you're part of the surroundings and you're absorbing the heat that was released from the system. In exothermic processes, the surroundings get warmer. In the last video, we talked about how heat is often represented by the small letter Q, and work is often represented by the letter W. Sometimes we use these as variables in equations, and when we do, there are certain sign conventions that we use. For heat, for Q is greater than 0. That means it's a positive number if heat is transferred from the surroundings to the system. In other words, Q is going to be positive if the system is gaining energy. And that's because we look at these variables from the point of view of the system. If heat is transferred from the system to the surroundings, if the system is losing energy, Q will be negative. Q will be less than 0. We see similar sign conventions for W. W is going to be greater than 0. It'll be positive if the system is gaining energy through work. In other words, if work is done on the system by the surroundings. W is going to be less than 0 or negative if the system is losing energy, if work is done by the system on the surroundings. When you form a solution by, for example, dissolving a salt, the formation of the solution may be an exothermic or endothermic process. And there are 3 main steps that occur when a solute is dissolved by a solvent. The first thing that happens is that particles of the solute have to separate from each other. This is an endothermic process. If we're talking about an ionic compound, in order to separate the particles from each other, we have to put in energy to break the ionic bonds. If we're talking about overcoming intermolecular forces in a non-ionic compound, that always requires energy as well. So that's endothermic too. So regardless of the types of particles you're separating, this is going to be endothermic. Now, another thing that has to happen is that the particles of the solvent also have to separate from each other. And this process is also endothermic, and that's because it takes energy to overcome the intramolecular forces between the solvent particles. For example, we're often using water as our solvent, and those water molecules are attracted to each other very strongly through hydrogen bonding. We're going to have to put in energy to overcome those very strong intramolecular attractions. The last thing that has to happen is that the particles of the separated solute and solvent need to combine to make the solution. And this process is exothermic. The process involves forming intermolecular attractions between the solute particles and the solvent particles. And forming intermolecular attractions is energetically favorable, and it releases energy. The overall energy of forming a solution depends on the magnitude of the energies of these different steps. If the energy absorbed during the endothermic step is greater than the energy released during the exothermic step, the solvation will be endothermic, and we can see it in this nice energy diagram. All those H's, the delta H's, those actually relate to a concept called enthalpy, which is closely related to heat, and we're going to be talking about that in a future lesson. But still, this all has to do with energy. Now, if the energy absorbed during the endothermic steps is less than the energy released during the exothermic step, the solvation will be exothermic, and we can see an example of this in this diagram. So in summary, you should now be able to explain the relationship between experimental observations and energy changes associated with chemical or physical transformations. You should be able to describe whether a change is exothermic or endothermic and the direction of energy flow.